Hi, I'm Professor Len Kelly, and in today's presentation I want to demonstrate how to construct a confidence interval estimate for the mean response and a prediction interval estimate for a particular response using an estimated multiple linear regression model. We've already introduced the multiple linear regression model, and of course the notation that we're using in our model, we want to make sure that we understand that P represents the number of parameters, and so in this particular model we have P minus 1 predictor, explanatory, or regressor variables. We've noted how we can model that multiple linear regression model using matrix algebra, and we discussed briefly how we might go about including qualitative variables into a multiple linear regression model. In fact, we looked at an example where we built a multiple linear regression model and found the estimated regression coefficients, where we were interested in the monthly housing payment being the response variable, and total debt, family size, location, income of the first wage owner, expenditures on utilities, and whether the residence was owned or rented as explanatory or regressor variables. And we highlighted the idea that location is clearly a qualitative variable. In fact, we had coded that variable 1, 2, 3, 4 in the data set that we worked with, and we'll see again today. We went on to discuss, let me just flash back a second, we went on to discuss that for that particular variable, since there were 4 levels, 4 locations, we only used 3 of the dummy variables to avoid the X transpose X matrix not having an inverse. Now, we'll have a lot more to say about qualitative variables as we make our way through the course a little bit later, but for now I do want you to recall that we went ahead and we built a multiple linear regression model using the variables family size, ownership, first income, utilities, debt, and the 3 dummy or indicator variables, loc 1, loc 2, and loc 3. And so we couched our interpretation of these estimated regression coefficients in terms of location 4, which is the southeast location, as being the baseline. And you might want to review that discussion from the previous lesson that I provided to you. Now today I want to work with the same data set but with a reduced model. In fact, if we go back to the multiple linear regression model that we built using all of the variables that we all of the regressor variables that we've introduced, you're going to notice that some of them might not be contributing significantly to the explanatory power of the model. And to illustrate that, let me go back to the output associated with that multiple linear regression model, in which we use the 8 regressor variables that you see here in the output. And you have this Excel spreadsheet. It's the payment MLR Part B solution.xls Excel workbook that I've already made available to you. And here's the output associated with the regression that we performed on that data. What I want you to notice, and again we'll have more to say about this a little bit later, but if you take a look at the 95% confidence interval estimates for the regression parameters associated with ownership, first income, and utilities here in the brown highlighted area, you're going to notice that those confidence intervals contain 0, and because they contain 0, we cannot reject the claim that those regression coefficients are in fact 0. That is, we cannot reject the claim that in the presence of all these other variables, that these particular variables taken one at a time are insignificant, that their regression coefficients might be zero is clearly in play. And it's because of that that I'm going to eliminate those three variables, ownership, first income, and utilities, in today's discussion. And so I want you to accept for the time being, and we'll, like I said, we'll have more to say about this later, but I want you to accept for the time being that those three variables, ownership, first income, and utilities, do not significantly contribute to the explanatory power of a model already containing the five other variables, debt, family size, and those three dummy location variables, loc 1, loc 2, and loc 3. And the reason I am eliminating them is because they really do not, as a block, add much to the explanatory power of the model. And we'll discuss this in greater detail in an upcoming lesson. The bottom line is I've taken the reduced model and I've fitted it. And the estimated regression coefficients associated with that model turn out to be this vector B that you see on this particular slide. And this model is highly significant, and it provides nearly as much explanatory power as the original model. Now here's our 8-variable model, and that model has an R-squared value of 0.53. You see highlighted here in blue. Highly significant, as we discussed during a previous lesson. Now, I ran the reduced model, and of course, you know, you can make your way through this workbook. In this particular case, I've eliminated those three variables that we discussed, and I've run the reduced model, and that's contained on this worksheet called Reduced MLR. And what you see here is an R-squared value of nearly 0.53. Again, go back to the full model where we included those three variables, ownership, first income, and utilities, and notice that the R-squared value there is 0.53. For the reduced model, the R-squared value is nearly the same. It's 0.529. And so we've lost very little explanatory power by eliminating those three variables. And of course, if we did an F-test on the overall significance of this reduced multiple linear regression model, we see that we get an F value of 111.35, and as importantly, maybe more importantly, a p-value of 0.000078 of them 1. And so this model clearly is highly statistically significant. And so we're going to work with this reduced model in an effort to demonstrate how to construct a confidence interval estimate for the mean response and a prediction interval estimate for a particular response given this estimated reduced model. So we're going to use this reduced model to find a point estimate for the monthly mortgage payment for a family of size 4 living in the southwest section of our neighborhood. And the southwest section was coded using location variable 1 as being equal to 1 and 0 otherwise, and we want this family to have $4,000 in debt. And then we're going to find a 95% confidence interval for the mean mortgage payment for all such families. And then we're going to find a 95% prediction interval estimate for the mortgage payment of a particular family having these characteristics. And so at this point, I want you to consider, what's more difficult to do? Estimate the mean response or to estimate a particular response? And we've discussed this previously, and I hope you agree that estimating a particular response is much more difficult than estimating a mean response. And the reason is that when we're dealing with means, the noise gets smoothed. Keep in mind the variance of x bar, our sample mean. Remember that from our basic statistics course. The variance of x bar, where the sample was taken from a population having variance sigma squared, the variance of x bar turns out to be sigma squared divided by the sample size. And so we know that the variability of a mean gets lessened, in some fashion gets smoothed, as compared to the variance of a particular observation that we take from a population. And that's important for us to remember. Now, let's go back. To estimate the mean response, of course, we know how to do that. We find our estimated regression coefficients. We take the values of our x variables that we're interested in. We include the 1 so that we can grab the intercept term b0, and we match up the values of our x variables against their corresponding estimated regression coefficients. We do that multiplication. We add. We can do that using the expression y hat equals x transpose times b. We've seen this before, and of course we know how to generate the point estimate associated with that particular levels of our x variables. That's an easy multiplication problem. And in this particular case, we're interested in a family of size 4 with $4,000 in debt, living in location 1, so our loc 1 qualitative dummy variable is a 1, loc 2 and loc 3 then are both zeros, and if we simply multiply the 1 times 512 and the 4 times minus 46.9 and the 4,000 times 0.09 and the 1 times 250 and the 0 times 360 and the 0 times 170, that is, if we do this computation of taking x sub h transpose times b, we get a result that is $957.58. So that's our point estimate for the mean response of a family of size 4 with $4,000 in debt, living in location 1. And of course we can do that on our spreadsheet. And I've done that over here in this brown highlighted section of our worksheet. And you see there, I've taken my x sub h column vector, I've taken its transpose, and then I've performed the arithmetic of that transpose times this column vector of estimated regression coefficients. Make your way around this spreadsheet to see, how all that's working, and convince yourself that a point estimate, that is y hat, is indeed $957.58. So that's our best guess as to what a family of size 4 with $4,000 in debt, living in location 1, would pay on average on average for their monthly housing payment. Now, to construct a confidence interval estimate for that estimate, we need to do the same kind of thing that we've done when we've built any confidence intervals. We take our point estimate and add and subtract some stuff to it. And the stuff that we add and subtract to it has everything to do with the level of confidence that we're interested in and the variability of the point estimate that we use to try to get a handle on what the average payment will be. In this particular case, it turns out that the standard deviation of y sub h hat is equal to the square root of x sub h transpose times that matrix that we've come to know and love, x transpose x inverse times x sub h, hit by our best guess for sigma squared, which is the mean squared error. And so if we find the standard error of our point estimate, multiply that by the appropriate t multiple that depends on the sample size and the number of parameters in our model, and do that computation, we can derive, here's a proof, by the way, that the variance of y sub h hat is in fact equal to sigma squared times x sub h transpose times x transpose x inverse times x sub h. Make your way through that proof when you have time, and you'll see that it falls out quite nicely. It's a little involved, but surely you can convince yourself that what we saw in the previous slide is legitimate. Now to build, we'll go back and we'll build this confidence interval for the mean response here in a few minutes. But let's talk about predicting a particular response. Now, when we try to predict a particular response, not only do we have the spread of the data itself to contend with, but we also have to contend with the point at which the particular observation that we're interested in falls. And so that adds another level of uncertainty to the problem. And so to build a prediction interval for a particular family having size 4, debt of $4,000, and living in location 1, we have more noise to contend with. We have more variability to contend with. And we can prove that the standard deviation associated with the estimator used for that prediction is the square root of 1 plus x sub h transpose times x transpose x inverse times x sub h, hit by our best guess for sigma squared. And we take the square root of that to get the standard deviation of our prediction. Now notice that we're going to use the same point estimate. We're going to use the same y sub h hat, our $957 and plus, as our point estimate, but we're going to add and subtract some stuff that accounts for the additional spread in our estimate. And when we do that, and we can do that in Excel, and if you go to this worksheet called intervals in the workbook called Payment MLR Part B Solutions.xlsx, you'll see that I've done that. And I've done it in a couple of different ways. And I'm going to ask you to take your time and go through this worksheet and convince yourself that you can do this kind of thing too. So here I've constructed my X transpose X matrix using my X matrix, which I've taken from this particular worksheet called MLR data reduced with a constant. Remember, you have to have that column of ones. And I would simply ask you, rather than me going through a bunch of details here and risking losing you anyway, I would ask you to simply take your time and go through these computations. So here's X transpose X. Here's the inverse. Here's X sub H transpose times X transpose X inverse. And then finally, here is X sub H transpose times X transpose X inverse times X sub H. And the t statistic in this particular case is associated with a alpha level of 0.05. We want a 95% confidence interval estimate. The point estimate, of course, we know how to get. And it turns out that when we take and do the arithmetic here, that is, we take our point estimate and we add and subtract some stuff to it, the stuff being the the stuff being the t value times the square root of mean squared error times X sub H transpose times X transpose X inverse times X sub H. When we do that arithmetic, we get a 95% confidence interval for the mean response of all families having size 4, debt level 4,000, living in location 1, as being somewhere between $909 and $1,005. Now that's a tight interval. And so we can feel pretty comfortable with that. But when we try to predict a particular family's monthly mortgage payment, we have that additional spread. And that additional spread manifests itself in an interval, a prediction interval, with a lower limit of $475 and an upper limit of $1,440. Now that's quite a spread. And so in this particular case, we demonstrated clearly that we can get a pretty tight estimate for the mean response. That is, our confidence interval estimate is pretty narrow. But when we try to predict a particular family's monthly housing payment, that is quite difficult. And that's evidenced by the breadth, the width of the 95% prediction interval. Well, there's a lot of arithmetic involved in doing this computation, and unfortunately, Excel does not, do this for us free of charge. And as a consequence, we have to do a little bit of manipulation ourselves. Now, in the workbook, the Excel workbook that I gave you, I've tried to make that simple for you, but it'll only be simple to the extent that you understand that workbook. So again, I would ask you to go through the worksheet called intervals and make sure that you understand how you can build a confidence interval estimate for a mean response and a prediction interval estimate for a particular response using matrix algebra. It'd be very important for you. The conclusion, well, the conclusion is, as always, take a look at the homework problems, take a look at the examples that are provided to you in your textbook, and most definitely comb through the example that I've illustrated in this particular presentation. Become an expert. There's no reason not to. Okay, until next time, this is Professor Len Kelly, and we just want to keep moving forward, onward.